All right, so today we are going to finish the DRAM lecture. The last component is the HBM, and then high bandwidth memory. So here, as you can see, is very important for today's AI and hardware system, right? So if you look at the GPU today, then we have a lot of HBMs integrated. So basically, HBM is something like this, right? You have many DRAM dies. So those DRAM dies are 2D DRAM dies. So each individual die is like a conventional DRAM die in a 2D fashion. But then we can stack many of them by this TSV and micro bump, as we discussed in the last lecture. So the key feature is that underneath this HBM stack, there is a base die here, which is a control logic die. So here you will have the I/O interface circuits and other timing control and other scheduling and I/O interface circuits with this physical layer, PHY, the physical layer. So all of those will be integrated on this logic die, which is called the base die. Okay. Then this is the entire HBM stack. You have a logic base die and multiple 2D DRAM dies. So then this is integrated with the compute, typically GPU. So then we will have this horizontal connection between the memory stack to the GPU. So this is routed through this substrate. And this substrate is actually is a silicon interposer. So this one is a silicon interposer. Okay. And then the entire interposer may sit on the package substrate. And then you have the conventional package boards to be bonded to the PCB. So here we have some like images under the microscope. So here you see this is the buffer die, which is the same as the base die. This is the logic die. So here you will have those a physical area. This is a control logic, including the I/O and timing and so on. And then the rest of the area is this TSV and then this ball array or the bonding. And then on the top dies, those are the DRAM dies. So the DRAM die, you have the memory DRAM bank, and those are the DRAM bank. And then in the middle, you have the TSV array. So this TSV array will talk to the TSV array underneath. So basically the communication between those DRAM dies to the logic die is through those vertical connection by the TSV. Okay, there are many of them. And some of them are used for the signaling. Some of them are used to deliver the power, like VDD, VSS. And even some of them are reserved for thermal, like thermal TSV, to basically extract the heat from multiple tiers. So there are many use of those TSVs, not only for electrical, but also for thermal. Okay. So then here, for example, this is some, so on the right, those are top views. Okay, if we peel off the top dies, you look from the top view, then you see this logic die. Okay, so then this image is a little bit different. This one is a cross-sectional view. It's like this cross-sectional view, but under the microscope in the real setup. So here you see the multiple DRAM dies, HBM, and then this silicon interposer, and then this is a GPU, and then this is a package substrate. So this is by TSMC's technology called CoreVerse. Okay, this is the mainstream technology for this HBM fabrication. So basically, the memory vendors, for example, Samsung, SK Hynix, right? And so they fabricate those HBM stack, and then TSMC will fabricate the GPU designed by NVIDIA, for example, right? Then it's TSMC's job to do this integration. They will get the HBM from the Samsung or SK, and then TSMC will do this CoWoS integration. So this is on the wafer scale. Okay. So then, yeah. So basically, this is the entire package. Okay. And one key feature here I need to emphasize: the HBM standard use a wide I/O. This is different from the DDR interface. So wide I/O here the connection, let's say, between the logic and then the memory will be on this wide I/O with 1024,000 bits. Okay, every time it will transfer 1024 bits as composed as opposite to the 64 bits in the DDR interface. So this is the key feature. Okay. And any questions here? Okay. So then, how do I hide this? Okay. So here, the HBM versus the GDDR5. This is like early generations of the HBM. You can see here this was from 2019, Samsung's presentation at IEDM. So it compare the GDDR5 versus HBM. So here, this is a system configuration. You have some processor, CPU or GPU, and then you can also do the packaging level integration with those GDDR5 with the processor on the interposer versus you do the HBM stack integrated with the processor. So here you see that here GDDR5 you will have like a 12 of those 8 gigabits GDDR5 chips, and then here you have 4 HBM stack, and each one is 4 gigabytes. So the total density right here is 12 gigabytes versus here in total 16 gigabytes. But you see the total package size get much reduced, right? Because here you have so many, those GDDR5, each is a 2D, you do not stack, right? So then the total package is more than 3,000 millimeter square. So this get a much reduction to about 800 millimeter square. And also the bandwidth increases because we had wide I/O. You see the bandwidth of the entire system improved by 3 times to like 1 terabyte per second. And then the power also get reduced. This is for the memory only. We didn't include the processor. Of course, processor will be hundreds of watts. Okay, for the memory a component, then the power also get reduced. Okay, so here the key is that actually for GDDR, they actually use 32 pins per chip, okay, instead of 64 for the regular DDR. GDDR, actually they may use just 32. But then each is much higher speed per pin. If you recall, the GDDR data rate per pin is higher. So like per pin is like 8 gigabps. And compared to the HBM, each pin is lower speed, but you have much more pins, right? So here, the wide I/O 1024, okay. So still, the overall bandwidth, you get the benefits. So for this simple comparison, you see the HBM-based system improve on every aspect. So that's the motivation to transition from the GDDR to HBM, especially for the high-end AI related workload. Okay, so then let me show you some like integrated system. Actually, the first product use the HBM was from AMD. It's not from NVIDIA. Okay, actually AMD did the first work. So the AMD's this particular GPU, this random R9 Fury X, uses Fiji chip, which is GPU chip, and then that one integrates the HBM, the first generation of the HBM. Okay, so then you have the GPU, and then you have 4 HBM stack co-integrated on the interposer. Then later, NVIDIA also adopted this scheme, and one an example is this V100 GPU system. And this uses the second generation of the HBM, and the total capacity for the HBM is there are two flavors. One is 16 gigabyte, one is 32 gigabytes. So the overall system bandwidth is approaching 1 terabyte. Okay. So then the latest product, H100, which is the most advanced GPU you can have today. Of course, NVIDIA is producing the next generation, which is B100, but that one is not on the market yet, even though they announced it earlier this year. But that's just the prototype. It's not in the volume production yet. So the latest one you can get is this H100. And then H100 uses the HBM3, the third generation. And then the total capacity is 96 gigabytes. And then the system I/O bandwidth is about 3.3 terabyte per second. And here on this graph, it shows the trend for the NVIDIA's system from the P100 to V100 to A100 to H100. And then here you see the HBM capacity on the left-hand side. As I said, so the H100 is close to 96 here, 96 gigabytes. And then the system bandwidth here on the right is 3.3 terabyte per second. Okay, so that's the latest result. So any questions here?
In the HBM generations, what exactly is changing? Like, let's say if we go from 1 to 2 to 3,
Okay,
what do
I'll
they
show you.
change?
Yeah, so this is a trend, right? So here, this is the density, or let's say the capacity of the DRAM system versus the bandwidth. And then here, of course, you can look at the DDR and the LPDDR and GDDR trend. But if you look at the HBM trend, so the general trend is to get more and more stacked layers in the 3D stack. So that's how you get the density improvements. And also you're going to get the bandwidth improvement as well. So you can prefetch more data, and then you can get the bandwidth improvement as well. So if you look at the HBM standard, actually this is good summary. The spec for different generations, right? So HBM1, 2, actually they have the 2E like extension, and the HBM3, and the latest I think is HBM3E. Okay. So if you look at the die density, right? That is each DRAM die is getting improved by the density itself due to the DRAM scaling. Okay, so this is each die's density. This is 2D DRAM. Okay, each die is a 2D DRAM. Okay, then due to probably this is like 2013, it's like a 20 nanometer technology node, and then to the 2016 maybe it's like 1X 1Y node, and then this is like the 1Z node or 1A node, and the latest one maybe 1B node or 1C node. So by the 2D scaling, then you get each die more density, right? More capacity. This is one way you get the overall capacity improvements. And then the other way is for the 3D system, you're going to get more and more layers. So they have this high, which means number of layers. 4 high means you have 4 layers of those 2D DRAM dies stacked. So then in HBM3, the latest is 12 layers stacked. Okay, 12 layers of the 2D DRAM stacked in that HBM. So then here you can get the data rate, and then the performance, and then the overall system like configuration, and you can look at, but still like IO is all 1024, okay, bits per, let's say, the in terms of the IO ways. I think the rumor says that the HBM4 generation, which is not there yet, but then I think they are going to change it from 1024 1000 to 2000, 2048. Okay, so they're going to double the IO. So what else? So yeah, that's pretty much the trend for the HBM. Okay, here is another view. In the graphics, you can see the total capacity on the left-hand side, and then the system bandwidth. Okay, and then 8 high to 12 high. So this is a general trend. So here, some more details on the packaging processes for the HBM. So we can go through this flow. So what you will do here, for example, then here we're going to first fabricate the front-end of line CMOS, and then you etch into the silicon to have a deep trench, and then fill with the copper. This is to make the TSV, okay? And then remove the copper and planarize the surface. And then here, then you finish the backend line processing, the interconnects. And then you get the bumps, those micro bumps, pad region. And then some solder reflow for the bump. And then after that, you have to flip the wafer, okay? You have to flip the wafer down because you are going to thin the wafer, okay, here. You're going to remove this bulk of the silicon. And then after you remove the bulk of the silicon, then you will expose this TSV to the outside. Then you will add this micro bump again, and then finish the wafer, and then you are going to remove this carrier wafer, and then you have this and also you dice this into those let's say DRAM 2D DRAM dice, and then you do the bonding, okay, chipped wafer bonding, yeah. So this is like the flow for the HBM. Let's say you can think here, what you are doing here is the single 2D DRAM die fabrication here all the way, and then make those bond ready, and also thin the wafer down, and then expose the backside, and then basically at this point, a 2D DRAM die is ready with those interface exposed for the bonding. So you do the bonding vertically by stack many of those. Okay. So yeah, this is the future generation HBM4. As I said, so they are going to increase the I/O to 2048 bits, and also they are going to integrate 16 high, which means 16 2D DRAM dies. Okay, and also they are going to switch from the micro bump to the copper to copper hybrid bonding. Okay, because if you recall the last lecture, the micro bump typically the bonding pitch is about like 30 micrometer. If you switch to the hybrid bonding, then the bonding pitch could be below like 5 micrometer. So you're going to further increase the bonding and density. And here are some nice view from the cross-sectional view to show this hybrid bonding. So there are many layers, okay, and then each of those is bonding pad, copper to copper bonding pad. Okay, so then the challenge for this kind of 3D system is always the thermal management. So here, where is the thermal risk originate from. So here you have the heat source. For example, here this is your GPU. Of course, that will become very hot. And then also the base die. Here, if you recall, the base die is a logic die, and that logic die has the I/O circuit. You are going to burst those bits out, right? So then this will also generate a lot of heat. So actually, the memory itself does not really generate too much heat. The DRAM itself, mostly, it's from this computer die, which is GPU, and also the base die, which is a logic control die. So then, how can we mitigate the thermal risk? Of course, you need the cooling, advanced cooling from the top. You need a good thermal interface material. And then, depending on the spec, you may use even active cooling. That means you may use liquid cooling, flowing through some microfluid on the package to further help. So here, as I mentioned, there are many thermal dummy bumps and thermal TSVs. Okay, many TSVs inside here, besides the signaling and power, many of them actually are helping to extract the heat from this base die to the top. Okay, because you have airflow or liquid flow from the top. So here, system level thermal design is important. This heat sink on the top, you have this heat sink, and whatever cooling, like air cooling or liquid cooling. So you have to co-design the entire system with the thermal management. So this is very important for the HBM-based system. Because here, the DRAM retention time will degrade at high temperature, right? Because high temperature, the leakage current from the transistor will increase, and then the retention time will decrease. So you have to mitigate the temperature impacts on the data retention. Okay, any questions? That's pretty much what we want to talk about on the HBM. Okay, so then the very last topic for the DRAM lecture. So we're going to spend a few slides on the embedded DRAM. So this is a little bit different from what we have discussed so far, right? So far we talked about the DRAM is all standalone DRAM, off-chip DRAM, including this HBM. It's off the chip, off the processor's chip. But here we're going to discuss this embedded DRAM. This is on chip, on the processor's chip. Okay. So this is not mainstream, but it's an interesting space, and that might become very useful for the future generations of the processor. So here, the idea is that we want to integrate the DRAM cell on chip. Okay, on chip memory mostly is SRAM and SRAM cache L1, L2, L3, and then SRAM is fast, but SRAM also is large in the cell size. You need 6 transistor or even 8 transistor, but it's very fast, right? Then DRAM, is more compact, but then it's not that fast. So also the fabrication, because it's cylinder cap, is not very compatible with the logic process, right? If you have a cylinder cap standing up, then there's no space to do the interconnect routing for your logic. For your logic processor, then you have this 15 layers or 16 layers metal routing. And then if you have the capacitor standing up, then there's no space to do the routing. So then here the concept embedded DRAM is to basically bridge the gap between SRAM and the off-chip DRAM. But this needs to be compatible with the logic process. Okay. So here, this is the target space because there's a gap, right, between SRAM and DRAM in terms of the speed, and then the cell size. So EDRAM is trying to fit within this gap. So the EDRAM technology was mainly used by IBM in many of their products. So for example, here, we mentioned the deep trench DRAM technology, DRAM cell capacitor before. And we say it's no longer being used for the standalone DRAM, but still is used for the embedded DRAM. This is true because here you can fabricate this deep trench in the silicon first, and then you fabricate your transistor here. So for example, here was an early work by IBM, and then this cell size for this 1T1C, it still is 1T1C, and then at 14.5 nanometer technology node, and the cell size is this number, and then this is smaller than the SRAM at the same technology node. Okay. However, the retention time is reduced for the EDRAM. So because this transistor is more like a logic transistor, right? It's not the specially designed. If you recall this recess channel or the saddle FinFET and so on, it's not that specially designed DRAM access transistor. So then the retention time is pretty short, right? Like tens of microseconds, because this transistor leakage current is not very low. However, this is compatible with the logic process because you can fabricate first the DRAM capacitor, and then you can go through the regular logic fabrication front-end lamp, back-end lamp process. Okay. So this is the layout for the EDRAM at this 45 nanometer technology node. It's 1T1C, so here is 1T1C, and here then we have to design the T a little bit larger, and then you have one of those contact via underneath that is a deep trench capacitor. So here, roughly speaking, the cell size is about 32 F squared. This is larger than the standalone DRAM, which is about 6 to 8 F squared. But this is smaller than the SRAM, right? If you recall the SRAM layout, it's roughly 160, even for the high density SRAM at this technology node. So this is still smaller than the SRAM. Okay. So IBM really invested in this EDRAM process over the generations. And actually they use that for their commercial products in their power series processors. And here, for example, the recent ones, like Power 8 and Power 9, based on the 22 nanometer and the 14 nanometer technology node. And on the same technology node, they introduced the EDRAM with this kind of cell size. So if you normalize that to like 22 and 14, then that will be like 50 or 80 9F squared. So it's still like 2 times or 3 times lower than the SRAM as a same technology node. And then the EDRAM is used as L3 cache in their processor. Okay. So L1 and L2 are still SRAM, but then L3 is EDRAM. Because still L1 and L2 is very fast. This EDRAM's read speed is about 2 nanoseconds, which is only good for L3 cache. There's no way to move the EDRAM speed to be the same as the L1, L2 cache below like nanosecond. So the DRAM fundamentally is still slower, right? But you get more density than the SRAM for the L3 cache. Okay. So here, this is the scanning for the IBM. Of course, later, IBM has a partnership with GlobalFoundries for the EDRAM and processes. So then they transition to GlobalFoundries. And then here are the pitch size and then the cell area, pitch size on the left, and the cell area on the right. for different technology node. Okay, so the last generation, I believe, is 14 nanometer, and then this is below like 0.02 micrometer square for one cell of the 1T1C EDRAM. So then Intel at one time also showed some interest in this EDRAM. And actually Intel introduced EDRAM process in their 22 nanometer FinFET right after they pioneered in the FinFET process, right? If you recall 2012, they first commercialized FinFET in 22 nanometer node. And then right after that, in 2013 and 14, they introduced this EDRAM process with the FinFET platform. So here, the difference is that Intel's EDRAM is using the stacked capacitor. It's not trench, okay? So this is a big difference. So you see that Intel's capacitor, this capacitor is standing up on top of the access transistor. So yeah, they use this capacitor over bitline architecture. And I don't know how they manage the thermal budget and so on. But they make it compatible, at least with this 22 nanometer FinFET logic processes. And here you can see from this cross-sectional image, the capacitor, like the aspect ratio, is not as crazy as the off-chip standalone DRAM, right? This aspect ratio maybe 5 or 7, 8. It's not like a 50, 60, 70. So that means the capacitance is not that high. Therefore, and also the access transistor is just a regular FinFET. Then the retention time also on the order of hundreds microseconds, as as opposite to the off-chip standalone DRAM, we have 64 milliseconds or even longer than that. So then this is one drawback for the embedded DRAM. So basically, your refresh cycle will be much more frequent. And here the EDRAM can generally operate random access with like a 3 to 5 nanosecond. But if it's in the like a burst mode, you can go up to 2 gigahertz. If you do not do random access, you do like a row to row, then you can be faster. So unfortunately, I think Intel publishes a paper, but actually never used this EDRAM in any of their products. Okay, and then after 2014, there's no follow-up on this process. So any questions? So I don't think today, after 2020, any commercial product use the EDRAM. Okay, before 2020, IBM's product, this Power Series processor, still use that. But after 2020, I don't recall anybody use EDRAM based on the 1T1C, because the retention time is too short and then the refresh overhead is too high. And then in the research community, there are many proposals to do the EDRAM instead of using 1T1C. There are other mechanisms to use it to work as DRAM. So here, there's one idea called the floating body EDRAM based on a single transistor. So basically, this is capacitorless. Okay, you get rid of capacitor. So there are many ideas to do the DRAM without capacitor. Okay, we call capacitorless EDRAM. So one idea is this floating body. This is typically based on SOI wafer. So you have the buried oxide, and then you have the floating body. So basically, when you apply like large drain current, then due to the electron will flow, right, and then you will have this impact ionization or the avalanche, or even the band tunneling. So basically, here near the drain junction, you will get the electron hole pair. especially at high drain bias. Then the electrons will go to the drain, and then the holes, if you recall, similarly to the radiation effects, the holes will tend to go to the ground, which is the body. But then for this SOI technology, there's no body, right? There's no body. This is insulator. So then the holes do not have the body to go to. Therefore, the holes will be accumulated in the channel, okay? Or this will raise the potential of the channel. And then you get higher drain currents. So that's your one state, okay? And then after some time, this holes will be recombined with electrons. Then this will decay. Then you will go back to the lower currents. So this is not a permanent state. That's why this is DRAM. There's a certain retention time for the holes to get accumulated, or let's say, before they decay. But this retention time could be like, microsecond, tens of microsecond to millisecond. So it's within the DRAM range. So this is how this can be used as the DRAM. And the benefit is that we do not have the capacitor, so that will ease the integration with the logic, right? The big challenge for the DRAM, conventional DRAM, to integrate with the logic is a capacitor. Either you have deep trench or have standing and cylinder cap, stacked cap, then that's not very friendly for the logic. So this is at least some proposal. And still, there are many challenges to design the EDRAM with this floating body effects. Like basically, there's like a coupling issue, cell-to-cell coupling, and then the retention and so on. So this is not widely used, but at least there's a concept like this. And then this 2D GaN cell become quite popular in the recent years, at least from the research community. And also our group, and also Professor Sumandata's group, and many others have been working on this. So here, the idea is to use two transistors, but in the GaN cell configuration, and to be served as DRAM. So here the idea is that you have two logic transistors. Then here, this is like a storage node. And you're going to get charge here by injecting the charge from this right transistor. This is a right transistor. This is a read transistor. So let's say if you write the data in, right, you have an electron, have charges here. Let's say charge, positive charge, okay. But actually electron flows the other way. But anyway, so let's assume this is positive charge. Then you're going to turn on this read transistor. So read transistor will have high current, high drain current. Or if you do not have the positive charge here, then the read current will be low from the read transistor. So you are relying on this amplification due to the transconductance of this read transistor to read out whether you are going to have the charge here or not as a memory state. Okay. So this is a DRAM because here the charge here will leak, right? You have this off current through this red transistor, and then the charge will leak over time. So it's not permanent. So that's why this is a DRAM. You still need to refresh. So here, this idea actually is not new. It has been there for 20, 30 years. At first, people try to implement this with a silicon front-end non-silicon transistor. So here in this column, we summarize some of those typical characteristics from the silicon-based 2D GaN cell. And the big challenge here is that because here you have the logic transistor, the off current actually is high, right? Compared to the DRAM access transistor. Therefore, the retention is also not good, like in hundreds of microsecond range. So they suffered the same issue as the 1T1C silicon EDRAM. But recently, there are breakthroughs in the technology to do this ultra low leakage transistor with non-silicon channel. So typically people would prefer to use oxide semiconductor channel. Okay, so there are oxide semiconductors like the IGZO, indium gallium zinc oxide, or indium tungsten oxide. So those are wide band gap material, and the leakage current is much lower than the silicon by orders of magnitude. Therefore, if you use those material as the channel transistor, as a channel for the transistor here, then you will improve the retention actually above the second. So you may not need to even refresh if you use this as a last level cache, because last level cache, you need to update the data anyway. So you just need seconds or minutes of the retention. So then this become very attractive, okay? So that's why here in the industry and also research community, there is a huge investment in this 2D GaN cell EDRAM based on the oxide semiconductor material. Okay, if you go to the IEDM conference these days, there are sessions with many of those kind of papers. So there's also proposal to stack, because right now here this is if you do those two transistors side by side, you still need to spend footprint by two transistor. There is a proposal to do this vertical channel transistor, so you can and have those two transistors stacked vertically. Those two transistors, one read, one write. This is a read transistor, this write transistor. So with those kind of oxide channel all around, then you can really shrink this to 4F square, and then the density could be even higher than 3 nanometer SRAM. Even the pitch here is larger than the SRAM. So there are many opportunities. And the challenge for this kind of design is that the stability of this oxide transistor is not as good, or reliability is not as good as silicon. So there are many challenges to be solved to make this really commercially competitive. Okay. So then with this kind of 2D GaN cell, actually the company Macronix from Taiwan proposed a 3D stackable DRAM based on this 2D GaN cell. And this is not for EDRAM. So this goes back to the 3D vertical stack DRAM we talked about earlier, right? If you recall the horizontal 1T1C. And then here, this one is to achieve similar target or density with the horizontal 1T1C for the 3D stackable DRAM, but with the 2D GaN cell without the capacitor. So here, what they did is to basically have those 2D GaN cell horizontally lined up, and then one write transistor, one read transistor, and then they can stack this with this multiple tiers using this kind of stack number sheet fabrication scheme. And then you can potentially get high density without the capacitor. So this is an alternative design, which was just proposed this year at the VLSI conference just 2 or 3 months ago. So there's another proposal from the same company. They had a different design using this gate-controlled thresher for the 3D stackable DRAM. So here, basically, they're going to have another sheet and then 3 gates. And then by changing the gate voltage, you're going to play with the band diagram along the source to the drain with the 3 gates. So there's a particular state you can achieve this notch-up effect with appropriate biasing condition. Okay, So basically, you can have the match-up effect by playing with the timing and the voltage of the three gates. Then you can create this positive feedback with these junctions. So without the gate, if you look at the typical called the PN-PN junction, if you have PN-PN junction, this is called the thresher structure. And then there's a particular state you can cause the positive feedback with the PN-PN junction. That will get your drain current high, okay, in that particular state. But of course, when the carrier, will combine with each other, then this current will degrade. So it's a temporal effect. But anyway, with this kind of a three-gate structure, they can achieve this kind of temporal or latch-up effect, and they can use that as a DRAM. So basically, if you have the positive feedback, then you have a temporal latch-up, and then you get more currents. And with the as the time goes by, then you have the recombination, the current will drop, then go to the other states. So there are many proposals. I just want to say that in the community, people are innovative to design the future generations of the DRAM for both embedded and also the standalone 3D stackable architecture. So this is a golden era for the DRAM research, okay? Just a quick summary. We talk about the DRAM, and I would say there's no memory that can replace DRAM. That means no existing memory or any new emerging memory that can replace DRAM. Because DRAM has unique combination of the speed and the cost and endurance. Okay, the speed, like a few nanosecond to tens of nanosecond, and the cost, the F square, and also let's say the total capacity. Right, nowadays DRAM is like 32 gigabits. And endurance, you don't have the endurance problem. You can read or write the cycle, the DRAM for many cycles. So there's no other any technology that can combine those three features together. So that's why DRAM is unique and not replaceable. Okay. And then the DRAM's recent trend is to do the HBM, right? The 3D stacking with TSV and microbump. And in the future, hybrid bonding, right? So that's why HBM becomes the enabler for GPU and in general the AI hardware, really because of the HBM. Okay. So for example, I said earlier at the very beginning of the lectures, the large language model today heavily depend on the HBM because the model size 1 trillion parameters, 1 terabyte basically. And then you look at the H100. Each H100 has 6 HBM stack, and in total, you have 96 gigabytes. Okay, then one GPU card, not enough, right, to hold the 1 terabyte model. That's why you need more than 10 H100 to run this 1 terabyte large language model. So here, then for the DRAM technology itself, even though let's say you have the stacking for the HBM, but each layer within the stack is a 2D DRAM. And then each of that is like today is like one C node, which is like 11 or 12 nanometer in terms of the feature size. So then how to scale the 2D DRAM below 10 nanometer is a open question. Okay. So that's why I say the DRAM industry is at a reflection point. Because people are looking into the 3D vertical stackable DRAM as we discussed in the lecture. Or maybe there's an intermediate step, which is to switch from the, let's say, 6F square to 4F square by using the vertical channel access transistor with those oxide semiconductors, potentially, like IGZO or other materials. So this transition will happen, I believe, in the industry. And then lastly, we talk about the embedded DRAM. This is another interesting avenue because this could potentially serve as a gigabyte level NAS level cache on chip. Okay, like your L3, or you can add a L4 cache with EDRAM, with those new flavors of EDRAM, for example, 2 gig NCL, for example. And then you can get like gigabyte level, NAS level cache on chip. That will help with many of those applications. So that's pretty much what we want to talk about for the DRAM lecture. Any questions? All good? Okay.